We're now going to talk about the effect of relativity and special relativity to the addition of velocity vectors. And this is actually where this all began, remember, with the Michelson experiment. When you look at a particular situation, for example, a kayak going down the river, if you wanted to measure the velocity of this individual heading down this river, you would be measuring his velocity as he generates it with his oars, but also the velocity of the river itself. And his velocity would be a sum of those two velocity vectors. So classically, if you have the top situation where a guy is pulling a little girl and he is pulling it at a velocity of 1 meter per second, and she throws a snowball at a velocity of 1.5 meters per second, the first velocity is designated v, the second u prime. To an observer, the actual velocity of that snowball, u, is 2.5 meters per second, a simple addition of the two velocity vectors. Conversely, if she throws it the other way, it's again an addition of the two vectors, but now it's 1 and minus 1.5. So what the observer sees is minus 0.5 meters per second. So classically, the observed velocity is equal to the velocity of the individual plus the velocity of the propelled object. But according to the experiment that led to the second postulate, light moving in a positive direction with regard to the speed of a car or in a negative direction, its velocity has no impact. And therefore, that classic vector addition is not actually valid. So relative vector addition is shown here so that the observed velocity is now not just equal to the sum, but it is equal to v plus the additional velocity as corrected by the effect of light and the fact that light is unaffected by the relative speeds of the two objects moving. And that's what this formula is. It's v plus u prime over 1 plus v times u prime over v squared. So we have an example here. First example is that we have v is a rocket traveling at a speed of 0.5 c that fires out a laser light, and since it's light, it fires at a velocity of c. And the question is, on Earth, what would be the velocity of this light as seen on the Earth? Well, this is kind of a trick question because, and you don't really have to use it because the light ray is, the laser light is light, therefore its velocity would be c. And so it would be unaffected by the velocity of these two rockets regardless of the direction that they're traveling. So it's actually a little, but if you put it in the formula, what you'll get is 1, and the velocity remains c. Now here's one where we can actually use the formula that we have. We have a rocket traveling towards Earth at a velocity of 0.5 c, and a canister is fired off the rocket at a velocity, let's say it's a torpedo. It's fired off a rocket at a velocity of 0.75 c. So to an observer on the Earth, in part A, if it both headed in the same direction, to observer on the Earth, what is the velocity of the canister? And then if it's shot in the opposite direction, what would be the velocity of the canister? So let's take a look at how we would do that. First of all, v is going to equal 0.50 c, and u prime is equal to, in the first case, a positive 0.75 c. So u is equal to v plus, and now the correction factor is like this: 1 plus vu prime over c squared. And so if we put the numbers in here, u is equal to 0.5 plus 0.75. Both of those are times, and this whole thing is times c. 1 plus 0.5c times 0.75c over c squared. Then u is going to equal 1.5 1.25 c over 1 plus, and if you do all this math in here, you end up with 0.375. So it's going to be 1.25 c divided by 1.375. So u in the positive direction is 0.909 c. Now the second half of this problem is very similar, except you have to change the sign. U prime now becomes negative 0.75 c. And you do the whole thing again, but have a negative in here instead. So you start out up here, you're going to have 0.25 negative on the denominator. On the numerator, it's now going to be 1 plus 0.5 c times a negative 0.75 c over c squared. So this quantity now becomes minus, so it's 0.25 c over, instead of plus, it's now minus 0.625, and you end up with a minus 0.4 c as the velocity. Now this has an impact on light, and that impact is called the Doppler shift. And you remember from our discussion in sound, we talked about the Doppler change shift. If the velocity is in the same direction as the travel, then the wavelength gets shorter, the frequency gets higher, and the wavelength gets shorter. That's called a blue shift. Conversely, if the source is moving away from the observer, then the frequency gets wider and the wavelength gets longer, and that's called a red shift. And so, depending on which direction you're going, it either gets longer or shorter. And the effect is that the observed frequency is equal to the source frequency times this correction factor, which corrects for the velocity of the source relative to the observer. And u here is positive if the source is moving away, and u is negative if the source is moving towards the observer. So if you have a galaxy moving away from the Earth at a speed of this, it emits a radio wave with this length. What is the new wavelength detected on the Earth? So what do we know? Well, first of all, we know that it's the velocity of the object of the source. It's going to be 0.825 c. We know the wavelength, source wavelength, which is 0.2525 meters. And we want to know what the wavelength is of the observed. The equation we need is the wavelength of the observed is equal to the wavelength of the source times the square root of 1 plus u over c divided by 1 minus u over c. And this is this way, so that 0.525 times the square root of 1 plus 0.8525, we'll just take the c's out, okay? 1 minus 0.825. And if you do that, you get 1.7 meters is the observed wavelength. Now, obviously, if it can affect velocity, it can also affect momentum. So there is relative changes in momentum at high speeds. Momentum obviously is important, but the effect can even be greater when taking relativistic calculations into effect. Classic momentum is P is the mass times the velocity, in this case m times u. But now it has to be corrected with a gamma factor, which we've seen before, and in this case gamma is equal to this 1 over the square root of 1 minus this quantity u squared over c squared. And that corrects for the effect of relativity. What is the momentum of an electron traveling at this speed? The rest mass of an electron is 9.11 times 10 to the minus 31. Well, we know the U is equal to 0.985 C. We know that the mass, M, is equal to 9.11 times 10 to the minus 31. Classically, we would just take M times U, but now we need to give the factor gamma. And gamma is equal to 1 over the square root of 1 minus u squared over c squared. So gamma is going to equal 1 over the square root of 1 minus 0.985 c squared over c squared. Now we know that the real momentum, relativistic momentum, is gamma mu. So we can take this and multiply it by that. And if we do that, we have 1 over the square root of 1 minus 0.985 c squared over c squared times the mass times .985, so that P is going to equal 1.56 times 10 to the minus 21 kilograms meters per second. This diagram just shows that as masses approach the speed of light, the relativistic momentum approaches infinity. And that this is one evidence that things with mass cannot actually reach the speed of light. The last topic we'll talk about is relativistic energy. Energy is, we know that one of the things that Einstein also showed that rest energy of any mass is equal to the mass times c squared. So the rest energy is this mass. It has this much energy if it's not moving. The total energy is the energy plus the correction factor gamma, where the correction factor is given in and is very similar to what we've already seen. So what would be the rest energy of an object that has 1 gram of mass? Now this is a very simple calculation. The rest energy is mc squared. In this case, it's going to be 1.00 times 10 to the minus third kilograms times 3 times 10 to the 8th meters per second squared. Now that's what this shows you is the enormous energy that a very small amount of material has, in this case, 9 times 10 to the 13 joules, kilogram meter squared per second squared. Now, the second problem here, a car battery is rated to be able to move 600 ampere hours of charge at 12 volts. Calculate the increase in rest mass of such a battery when it is taken from being fully depleted to being fully charged. Well, what do we know here? Well, we know, now this is a little bit more complicated problem, but we know that I is equal to 600 amps. We know that V is 12 volts. And we know that C, obviously, is 3 times 10 to the 8th meters per second. What we want to know is the change in mass. The appropriate equation here is that the change in energy is going to be equal to the change in mass times c squared. And so the change in mass is going to equal the change in energy divided by c squared. So the change in mass is going to equal to the electric potential energy divided by c squared. And that's going to be equal to QV over c squared. And Q is I times T is equal to Q times V over c squared. And we have numbers for all of this. IT is 600 amps per hour, 12 volts, divided by 3 times 10 to the 8th meters per second squared. So if you do all this and change hours to seconds, then you end up with an answer of 2.88 times 10 to the minus 10 kilos. You have to change, this is amps per hour, you have to multiply this by 3,600 seconds. And once you do that, that gives you proper units, and you end up with this as the change. This diagram shows the effect of the speed of light on relativistic kinetic energy, and this also shows the fact that objects with mass cannot reach the speed of light. And here again we have a calculation correction to form the relativistic kinetic energy. And here's the statement: thus it is not possible for an object having mass to reach the speed of light. We have an extra problem here. I'm going because of the time involved, and we're really out of time at this point, I'm going to let you all do the calculation here. It's fairly straightforward. Also, the answer to this problem is in your book on page